Hi, NA Physics, it's Mr. Neff. Hey, we're going to do some examples with displacement and velocity today. And before we do you know what happens when race car drivers eat too much? I'll tell you about them at the end of the video. A first example here, we have a couple walking 3/4 of the way around a circular lake, radius of which is 1.5 kilometers. They start at the west side of the lake, so they're going to start over here. And they go south to begin with, and they're going to walk 3/4 of the way around. So we're going to do that. Now, what I just drew there represents the distance. And so in part A, they're asking what is the distance that they travel. Pause the video and calculate that. So if I wanted to calculate the circumference of this, I'm going to do 2 pi r. So that's going to be 2 times pi times the 1.15, which is going to give me 9.42 kilometers around there. Now they're only going 3/4 of the way, so I need to get 75% of that, or 0.706. Now, significant figure-wise, 3 of those are significant. 3/4 is written out so that they don't want you to use that as significant. So I'm going to go 0.70, technically 7 kilometers there for the distance that they walked. Now in part B, they want to know the magnitude and direction relative to east of the couple's displacement. The displacement is going to look a certain way. And I'd like you to pause the video, I'd like you to draw the displacement, and then I would like you to try to calculate that displacement. All right, so displacement looks like this. I drew from the starting point to the finishing point. I drew it as a vector, and that's 2-dimensional, so I'll call it delta r. Now, how big is that? Well, it goes something like so. That's 1.5 kilometers. That's 1.5 kilometers. And that's a isosceles right triangle. So I know a little trick that I could say that the displacement's size is 1.5 kilometers times the square root of 2. If you do that, you end up with 2.12 kilometers. If you didn't know that square root of 2 trick, you could just use Pythagorean theorem on that. You get exactly the same answer. Now, they also want the direction. So we need this angle right here. If you didn't calculate that, pause the video and try to calculate that. You're going to do an inverse tan of, well, 1.5 kilometers over 1.5 kilometers, which is essentially 1. You'll see on your machine that that's 45 degrees. 45 degrees on the north side of east. So we have a magnitude part and we have a direction part. A question follow-up on this would be, did the couple get their shoes wet? Well, the answer is no. They walked actually on the red path, but what they did was just as good as had they have walked through the water, swam across the water, what have you. The blue is the effect of what they did. The red is what they actually did. Here's an example. A car makes a trip due north for 3/4 of the time and due south for 1/4 of the time. The average northward velocity has a magnitude of 27. The average southward velocity has a magnitude of 17. What's the average velocity for the entire trip? So this car is going to go north for 3/4 of the time, the total time of the trip, at a pretty fast speed. So they're going to go pretty far. Maybe this is it. Okay. Then they're going to go south, slower, and for only relatively 1/3 of the time. So not that far. So something like that. Now they want to know what's the average velocity for the entire trip. So what I'd really want to do, average velocity, is displacement. I'm putting y because I drew it that way. Displacement over time. So I need this yellow displacement right here. That's the total one. And divide by the time. Now you might be thinking, they don't tell me the time at all. So hopefully there's something that cancels out. So now what I want you to do, I want you to pause the video. I want you to try to come up with how far this blue is, how far this yellow is, and it's going to have to be an expression, and then we're going to subtract the two and then divide by the time. Go ahead and pause the video and give it a shot. All right, so each one of these displacements are the velocity for that part times the time. So we know that displacement is average velocity times time. That's going to be for both parts. So for the blue part, I'm going to say that this is equal to 27 meters per second times however much time that was. Well, they said that was 3/4 of the time. I'll just call it t. So now 27 times 3/4 is 20 1/4 t. So that represents how much distance that is. And similar to that, the red one is that distance times time. So I'm going to make it 17 meters per second times 1/4 of the time. And that's going to be 4.25 t. Now, the yellow then is the difference between those. So this yellow delta y is going to be 20.25 t minus 4.25 t. So the 0.25's cancel out, 20 minus 4, 16 t. So now, you might say, well, that's an expression. What am I going to do with it? Well, I'm going to do with it what I was going to do with it. I was going to put it in here and divide it by time. So it's the finish of this is as simple as 16t divided by t. Looks like it's 16 meters per second. Now that's the magnitude part. They want the direction part too. My picture shows that goes north. There you go. Now this is a neat example right here about baseball or softball. It says just after hitting a home run, a baseball player rounds the bases at a constant speed. The bases are d apart. And depending on what level you're talking, they might be 60 feet, or they might be 70 feet, or they might be 90 feet. And my picture here is 90 feet, like the varsity would be, like Major League Baseball would be. And it says the player takes t seconds between bases. It says always beginning from home plate. What's the player's average velocity and average speed as he touches first base, second base, third base, and back to home plate? Okay, so now, we're going to take these one at a time. When the player touches first base, his path looks like that, and his displacement looks like that. Delta R, so that yellow one's the distance covered and the delta. Now, if I want to calculate, like they say in part A, his average velocity and average speed. Let's do the average speed first, which we know is distance divided by time. So he's gone 90 feet. That little tick mark is feet, if you're not familiar. And the time, you know what, let's make it easy. Let's make a time in this case equal to 10 seconds. We'll say it's 10, 10, 10, and 10 for all four of the base paths. So 10 seconds. So this looks like this is going to be nice and easy. 9 feet per second. Yeah, I mean two significant figures on those, and the 90. The 90 is actually a lot of significant figures. That's measured out really carefully. The velocity is going to be a similar thing, and that's going to be the displacement divided by the time. So now this time, actually, I'm going to erase that arrow off the top of the velocity because they want. I just want the average velocity's magnitude in this case. And so I'm going to erase the arrow off the top of this displacement as well. And so I'll say that's, 90 feet and 10 seconds. And that means 9 feet per second. Right? Yeah, I mean, if you wanted to put a direction on there, it could be at first base. All right. So now the player is going to round first base and come over to second, and there's going to be a time like that. So for that whole trip, the whole yellow, everything I'm showing, not just the additional, but from home plate all the way, what is the average speed and what is the average velocity? I want you to pause the video and try to calculate that. Okay, so now for part B, the average speed, distance divided by time, well, they've gone 90 and 90. They've gone 180 feet. But it took 20 seconds to do that. And so it looks like that's still going to be 9 feet per second. Now, here's where people go wrong sometimes. When you're calculating the average velocity, it's displacement divided by time. The displacement isn't just 10 or isn't just 90 feet more. This is a displacement now. So from home to second base, this was a displacement, starting point to finishing point. And so it turns out you can see that there, that's 127, I'm just going to leave the inches off, 127 feet divided by 20 seconds. So that looks like that's only going to be 6.3 feet per second. See, the magnitude of the velocity is smaller than the displacement. Why? Because you change direction right there at first base. Hey, we're going to do that for third base now too. So will you pause the video and try to do both of those for third base? All right, we're back. So now the distance to third base is going to be another 90 feet. And so it looks like it's going to be 270 feet and divided by 30 seconds. And that's 9 feet per second, just like before. Now the displacement is right here. And here, some people go wrong here too, because they say the average velocity displacement divided by time. Well, the displacement is, 90 feet. That's true. But it took 30 seconds to get over there. And so, not 10. And so, whereas people want to say, oh, it's the same as it was at first base sometimes, it turns out it's only 3 feet per second because it took a long time to get that 90 feet away from home plate. Okay. From home plate all the way back to home plate, will you do this average speed and average velocity? Pause the video, please. Okay, and we're back, and we have distance divided by time, and the distance is 360 feet divided by 40 seconds. Hey, that's the same old 9 feet per second. Well, I mean, of course they are. It said that the person is moving at a constant speed. So, I mean, in retrospect, what did you expect? Now, the average velocity, though, if I go to try to draw the displacement, I'm going to draw from home plate and I'm going to draw to home plate. I get nothing to draw. So when I take the displacement, which is actually 0, and divide it by, I don't care what you divide it by, right? 40 seconds, technically, you're going to get 0. Does that mean that the runner didn't go? Does that mean that the run doesn't score? No, that's not what it means at all. It just says that the runner's motion resulted in no movement, no displacement, no change in place. So there you go. I'm just going to zoom that a little bit for you so you see what that is. I know some of that went off the screen last time. And before we go, what does happen when race car drivers eat too much? Of course, they get indigestion.